Hello, everyone, and welcome to today's session of the Ask the Expert series with Altair. I now give this time to our expert to proceed with the presentation. Thank you.
Yeah, in this session, we'll be talking about the radome antenna design using newFASANT. Radomes are nothing but radar domes. These are the protective structures for the antennas and associated electronics from the surrounding environment and elements such as rain, snow, ultraviolet light, and strong wind. The word radome is derived from radar and dome. They combined the radar and dome and they made the word radome. And the main applications of these particular radomes are in the aviation, telecom applications, and also you can find in military and civil radar applications, maritime communications, aviation, weather radar, satellite communications, coastal surveillance, SATCOM applications, automotive, air traffic control, vehicular, missile. Yeah, you can think of any application over here. Yes, for wherever you have the antennas, then definitely we can think of some kind of radome structures to protect them. And these are the solver methodology that is available using PICO based on the structural dimensions and the number of layers. We did propose, you can see over here, method of moments, volume equivalence principle, method of moments with planar means function. Also, FEM is there, ACA is there, how it is, when the dimensions are going up, we are taking the solvers. And also, once we have done the ACA, we are going ahead with the MLFM solver. And after that, we are going to use the multi-layer and FSS radiums where we'll be using the relaunched geometric optics solvers. We did have a detailed session on these particular solvers in one of the sessions. We did discuss about these particular solvers in detail. Then the radomes are classified into broadly based on the wall structure. The following types for the classified wall design. We can think of half-wave wall, thin wall, again in half-wave wall and thin wall. We can think of all these particular monolithic, laminate, and inflatable. All these options that are available in radome structures. And not only that, if you can think of the other section like A sandwich or B sandwich, C sandwich, multi-layer and graded radomes. In A sandwich means A sandwich is epsilon 1 is greater than epsilon 2. B sandwich is epsilon 1 is less than 2, epsilon 2. And C sandwich is epsilon 1 greater than epsilon 2. And how the combinations you can see on the right hand side, right? Epsilon 1, epsilon 2, sandwich, epsilon 2 sandwich between epsilon 1 and epsilon 1. And similarly, for the C, you can see over here epsilon 1, epsilon 2 is sandwich epsilon 1, but it is a multi-layer structure. Okay, this is how the radome layer setup will be made. Okay, then the session is open for the demo, and I'll be demoing the dual radome with double layer and FSS at 14 gigahertz. First, in this particular process, first step is I would like to go over with the FSS structure. So unit cell, I would like to consider that particular thing at 14 gigahertz and make sure that it's working at 14 gigahertz. Then, of course, we will be having this particular unit cell should be mapped onto a curved surface of the radome. And if you can see over here, radome, interesting fact is radome will be consisting of two sections, with lower section with single layer and upper section with FSS on inner side and double layer radome. That is the unique properties of the radome structure. Once we project this particular, as I told you, as I mentioned, I'll be designing the FSS using a tool that is available in newFASANT, that infinite planar periodic structure. Of course, as I told you, it is also working at 14 gigahertz. After that, we are going to project this particular thing on an inner radome interface. A volume is created with the extrude normal operation in case if we are interested in, which is shown in this particular figure. Okay, let me jump on to the demo part. You can see over here, most of you folks are aware of FICO launcher. You can see over here, like we have FICO, and of course, we, as Dr. CJ mentioned, we acquired a couple of more tools recently. In 2020, we acquired newFASANT, and of course, recently we acquired RAP. newFASANT is over here, and let me launch the newFASANT and look into the certain stuff about the solvers portfolio that are available in newFASANT before heading into our demo part. You can see over here this is the portfolio of solvers that is available in newFASANT. You can see method of moments are very good for radiation problems. Of course, Montrose module is very good for RCS problems. And there is a GTD solver is available where it is useful for shadow region effects can be studied effectively using this particular solver. And in this particular module, we'll be using the periodic structures for our analysis purposes. Okay, with this, let me jump on to open the unit cell, which I already had this. Let me open this particular Radome unit cell and bring the unit cell over here. That is FSS structure, frequency selective surface. You can see over here, this is the frequency selective surface. Basically, it got a wire mode, and of course, let me make it more elegant using the shaded option that is available in this particular GUI. Okay, you can see over here, basically, we took a metallic plate and we embed the cross structure on the metallic plate. That means we have a air and metallic interface, metallic region over here. Okay, how can we access this particular thing? Let me go ahead and go to the cell options. All these options are available in the cell. You can see over here frequency selective surfaces. It's not only just the strips. You can also select rings, strips, crosses, any shape you want. You can get this particular thing from this particular FSS primitive cell. Okay, as I mentioned, I was using a cross structure that needs to be embedded on the metallic plate. You can see the green regions, okay, highlighted green regions over here, okay, XYZ location, and of course size A and size B, which can be chosen appropriately so that you can embed that particular cross structure on the metallic plate. Okay, once I have this particular thing, you can see over here two dots beneath the FSS structure uh, that can be found over here. Define cell. If you can see over here, if I go to the cell, define cell, you can understand what are the layers, because basically we want to have the layers that are supporting the electric layers that are supporting this particular FSS structure. Here we have you can see from bottom to top, otherwise uh, interface 1, interface 2, interface 3. That's how you can read it. And we assign the materials Roha cell and epsilon 4.3 over here, and it got a transmission properties along TX and TY is 9.2 and 9.2. And basically you'll be having a radiation coming from the plane wave radiation plane wave source, which is going to excite this particular structure from the top of this particular thing. Otherwise, in the real case, what we are going to do is we'll be having the structure like this, and we'll be exciting the structure using the antenna beneath this particular unit cell. Okay, and this is about the unit cell construction. Once we have this particular unit cell, we can go ahead and we perform the simulation. Basically, we would like to perform the simulation from 4 gigahertz to 24 gigahertz in 21 samples, and so that we can study that where it is exactly resonating this particular structure. Okay, and then we have the solver option is there. We can choose the direct solver option to solve this particular problem. And then I can also go ahead with the meshing. We can create the mesh. Since it's already solid model, I can go ahead and visualize the mesh, how it is going to look. Okay, let me go to the 14 because it has 21 steps. And you see over here, this is the mesh file at 14 gigahertz, and you can see the multiple unit cell just replicating the infinite cell. That's why it is showing the unit cells, neighboring unit cells as well over here. Once we have the meshing part done as well, then I can go ahead and calculate the execute part. That's it. It is going to perform my simulation based on the course that you can choose the number of cores based on your system requirements. Since I am running on my computer, I can use my 16 cores that are available on my machine. Once I have this particular thing, then once I execute, okay, if you observe this particular workflow, similarly like in FICO, we are going the same fashion like left to right. Okay, left to right, we constructed the geometry, and then of course we define the unit cell over here. Then we do have the simulation properties, solver properties, meshing, then calculate. Of course, so that's what we are going to perform the simulation. Then I'm going to look into the results of this particular simulation. Okay. Okay, I got my S11 or transmission coefficient, reflection coefficient over here. Similarly, I would like to add the transmission coefficient of this particular unit cell over here so that to understand the characteristics of this particular unit cell. You see, with this, we actually I have a promising unit cells structure for the FSS array, and so that I can take this particular unit cell, export this into knob surfaces, and I can import this particular unit cell into my real radome problem. Okay, you see over here, if you observe, it is working at 14 gigahertz exactly. Okay, then let me go back and open the other model, radome model over here, which we are going to work with that. Let me open the, it is taking a little while, that's fine. Yeah, it opened. Now let me open the radome problem. Okay, let me go to the desktop and let me bring my radome demo model over here, because it already got all the necessary horn antenna, conical horn antenna, and radome structure. Before going ahead with the FSS structure, I would like to explain what does it have. Okay, let me show you what. First, let me go to the edit, manage layers. Okay, so that we can understand all the things one by one. Okay, in case if you want, you can see over here, we got a radome layer 1, radome layer 2, and of course we got a conical horn antenna. There are certain things that are not available, that cannot be visibly shown over here. That is got Cassegrain. This is basically a Cassegrain reflector antenna that we are using for this application. Let me go one by one. Let me deactivate these things so that we can use. This is the conical horn antenna which I would like to use for the exciting the radome. Then I do have the Cassegrain reflector. We can see a slot over here so that the radiation can come out of this particular reflector. So that there is a slot on the reflector 1, you can call, and also reflector 2 over here. And also we do have a metallic stands that are going to support these two reflectors over here. Then let me activate my radome 1 structure, and let me deactivate the feed and Cassegrain so that we can get the better feed of this particular structure. And you can see over here, let me zoom in so that we can see over here. If you observe, there are 3 interface layers. We will see how we are going to leverage these 3 interface layers. If you see in our unit cell, you do have a FSS structure. Unit cell is there. Then beneath the 2 layers are there. We are going to basically, what we are going to do is we are going to embed on this particular FSS structure. We are going to embed on this layer 1. Then we'll be defining a interface to a material 1. And also we are going to define a material in between over here. Okay, that's what we are going to do. The next step, let me activate the radome 2 and let me show you what we got. Here also we have like 2 layers. Let me zoom in a little bit so that we can get a better feel of this particular thing. You can see it's re-interface 1 or interface 2. You can see over here 2 layers are there so that we can define a material here in between these 2 interfaces. Okay, with this we understood what we got in our newFASANT GUI. We imported, as I mentioned, we imported a Cassegrain reflector antenna with a radome structure. Then we can go ahead and import our unit cell, which we worked on in our earlier case, which is working at 14.5 gigahertz, 14 gigahertz approximately. Let me bring my FSS unit cell now. Go to geometry. Import. Natively, newFASANT supports NURB files. Apart from that, it supports IGS step files, STL files, etc. You can see over here all the file formats that are supported in newFASANT. They are getting displayed over here. Then let me go to the desktop and get the stuff over here. Which we are looking for the unit cell. Yeah, as I told you, this is the unit cell which we exported from earlier case. And this is going to help us to generate the frequency selector surface now. Okay, once I have it, let me deactivate the other thing so that we can look into our unit cell coolly. I don't want the Cassegrain reflector as well. Let me have my radome 1. Okay, and I don't want the feed as well. You see over here. Now, if you observe this particular thing exactly at origin, we do have a FSS structure. And The efficiency of this particular simulation is that we're mapping this unit cell onto the curved surfaces. As Dr. CJ was talking about in this particular presentation, in case if you would like to map this particular FSS unit cell onto the curved surface, it might take a day or two, which is very easy using the newFASANT. Automatic mapping is available. Just couple of clicks, you can map this particular unit cell onto any surface. Here we are going to show you on a curved surface. Okay, let me go ahead and start working with the mapping the surface. Uh, Go to the geometry edit view, go to the edit option and go to the geometry options. Then there is an option called arrays on array surface. We are going to use this array on surface option to uh, to map the surface onto the interface one. Okay. Before that, I would like to explode the interface one so that it is easy to perform the operation. Okay. Radome one. Just let me take the Radome one interface one and let me explode this particular surfaces. You can see over here. Once I have exploded, I'll be having 4 sections that are available on this particular interface. 1, 2, 3, and 4. Okay. Once I have all these 4 interfaces, then I will go to map this particular thing onto the interface one. Okay. Let me select all these 4 interfaces. I know that's where I would like to map the surface. Go to edit. As I already showed you, use the geometry operations. Go to arrays, array and surface option. And then it is asking asking for a couple of options. Select array mode. What kind of array mode? For the time being, I will be using projected option. Of course, there are 1 and 2 and 4 are there. I would like to go with number 3. That is much more efficient for me. And this is asking if you pay attention to the command window. I'm punching the options over here. Do you want to project the FSS onto the surface bounds? No, I just want to, because if I ask to perform this particular thing to project on the FSS onto surface bounds, there is a chance that it can come out of this particular radome one. That's why I don't want that particular thing to be projected outside of this surface bounds. Then just plus S, and it is asking what is our array type, because we know from our unit cell structure it is a capacitive nature, because we got a metal and the air interface. It can be capacitive. It is capacitive. Then it is asking for the size of cell structure, and we know it is 9.2 and 9.2 that we got from the unit cell. And it is asking which unit cell needs to be mapped onto what is the element, planar element that needs to be mapped onto the surface. I'm going to select the object. Okay. So that once I select that particular unit cell, then I just need to hit enter. And you can see here how quickly it is generating the array onto the curved surface. You see over here, I got my FSS surface onto the interface one. Let me go ahead and delete the unit cell which I imported, because we no longer require that one, because we already mapped this unit cell onto the radome one interface. Okay, and I'm going to right click this particular unit cell, and I would like to delete this particular unit cell. Okay, let me make it available, all the things I would like to show, so that we can view the complete structure. Now we can see over here the complete picture of this particular one, Kissick rain reflector antenna with radome structure. Once we have this particular mapping done onto the curved surface, the other important part is we need to define the radome material, right? The interface where we are talking about the 3 interfaces are there. We need to mention about what are the materials are there in between the interfaces. Okay, go to the source tab, go to radome and define interface. Okay, and basically, as I showed you, we do have 2 radomes. I will be defining the 2 radomes over here. And in radome 1, I will be having 3 layers, right? Let me choose. Let me add the third layer over here. Okay, and let me assign the materials and the FSS elements appropriately in defining my radome definition. I will be choosing radome 1, all the radome 1, and I will be selecting this particular interface 1 objects. Okay, Similarly, I would like to select the Radome 1 interface to, and I would like to assign this particular thing to this particular second interface. Then I have Radome 1 interface 3 need to be assigned to interface 3. I have my interfaces assigned. Now I would like to tag the materials to this particular Radome interfaces. I know you can see bottom of this particular one, interface 1 to interface 2, interface 2 to interface 3. I have the FSS cell, then I know it is going to be ROHA cell, then after that epsilon 4.3. Let me tag the material. Just I need to find the ROHA cell. I need to go to the R. It might take a little while behind. Yeah, I got my ROHA cell available, and this is the ROHA cell in between these two interfaces. I have the ROHA cell with the material, and in this particular case, I'll be using the material with the dielectric constant 4.3, EPS 4.3. Okay, epsilon with dielectric constant 4.3. That's what I would like to assign. Then I need to, as I need to tag the FSS mapped surface, I would like to map now to this particular interface one. That's where we have it, right? I'm going to select this particular mapped FSS surface so that I would like to have this particular set FSS elements so that it will be available for this particular interface one. I defined my radome 1, the top section of the hemisphere. But now that I'm going to jump onto the bottom section to define my interface 2. Okay, I'm going to go to the radome 2, interface 1, set objects. Similarly, radome 2, interface 2, set objects. Okay, I would like to select this particular thing and I wanted to assign EPS 4.3. Okay, I assign this particular thing and everything is there. Okay, I can calculate the antenna results while doing this particular analysis. Yeah, okay. I set up my radomes. Now that I set up my radome structure and the automatic mapping of my FSS unit cell, this is the important part is done. I can jump on to solver thing and let me understand what we are going to do. We are going to solve this particular problem using method of moments. And also we do have a couple of options that are available in solving this particular problem like OpenMP. OpenMP is where we can solve this particular problem using on a conventional cluster machines. It works very well. In case if you are going to solve this particular problem on a cluster, we can use hybrid MPI plus OpenI MP architecture. Similarly, we do have EFIE, MFIE, and CFIE. Yeah, electric field integral equation. We did select that particular thing. Then I do have solver functions, subdomains, and macro basis functions. In case if we have a geometry with large number of unknowns, then definitely macro basis functions will be helpful. Also, Dr. CJ was showing in his slide how efficient in terms of the computational resources. It's almost half of the time you are going to get the results. Okay. Then we'll be having a 3D radiation pattern that needs to be computed with an angular step of 0.5 degree. This is once we have done this particular thing, I would like to go ahead and open I already solved this particular problem and I'm going to open the results so that if in case just go ahead with the mesh the geometry and then create mesh and we can select all the necessary mesh elements over here, then calculate, then execute. We'll be having how many process we are going to choose and we can run the simulation. Okay, just execute this particular thing. Just to avoid this particular thing, I would like to go ahead and open the already an existing model that is available with me. I would like to open this particular thing. Okay, you see over here, this is already solved. This is the same problem which I already solved this particular thing. Let me show the results first. Okay, let me show the mesh, how the mesh looks over here. Visualize existing mesh of this particular thing. That's the first step, right? We will mesh everything, then we'll want to solve this particular thing. And it is going to pull my mesh over here. You see over here, you got the mesh geometry of this particular model. And you can see over here everything. Of course, we're not able to see the FSS elements. That's fine. Okay. Then I would like to plot the results of this particular problem. Okay. Then let me go to the show results and plot the view cuts. You see, this is the results that are available for our radome. structure with the conical Cassegrain horn antenna. I would like to add the antenna results to this particular result. Okay. Okay. Add results. This is how it looks. Okay. We can also plot gain and total gain and everything. We can also do that one as well. We can see over here, this is the total gain. Then I would like to add antenna results over here. Okay. Let me add this particular thing and I want to deactivate. Yeah, this is what it would got. Okay. Then I can plot the uh, cut by frequency, view cuts by frequency. Also, we can do that particular thing. We can do that as well. Okay, you can see over here, I plotted the gain with respect to frequency, and I would like to add the results of the antenna. Okay, this is the antenna results, and of course, we had gain got decreased with a couple of 0.5 dB approximately. And also, in case if we want to add much more color to this particular thing, you can add points over here so that you can look into the points as well. Yeah, apart from that, there are some additional important parameters that needs to be looked in when we are evaluating the radome analysis. Those are nothing but the insertion losses. You can see over here, I am asking to get the insertion losses. You see over here, we have an insertion loss of 0.45 dB at 14 gigahertz due to the radome structure. Similarly, there is another important parameter called bore site error. You can see over here, the bore site error is not that significant. It just basically tells us how much the beam got deviated from the original beam due to the insertion of the radome structure. There is a chance that the main beam can be deflected, deviated to a certain angle. But luckily here in this particular case, we don't have any deviations available. Yeah, this is a very quick demonstration. You can see over here, this might take a day or two in case if you would like to do this particular analysis on any on the tool. But in newFASANT, we could able to automatically map the surface in no time, and then we can perform the study radome with the Cassegrain horn antenna reflector in probably like 2 to 3 hours of time. We can do it from scratch to end.
Thank you for the presentation. Before